last year, like maybe around December time frame, that like that we had like a conference in Japan about RISC-V, and then somehow some of the people like back in Japan actually got interested in like starting some sort of like that the special like a very specific region specific project for RISC-V. So what we did was like one of the like we went over to like that go to like all the IDMs, and then one of the questions, I mean, like they raised like many questions. Does it have MMU? Does it have L1 cache, L2 cache, that sort of stuff, like maybe 10 items. But one of the things that we noted that was probably missing more than anything else was like security, trust zone and whatever. And then that's the kind of response that we have got. So what happened was, so it happened that between like maybe 2003 and then 2008, we were working on the security, like maybe me and then Murthy, who's sitting over there. So we decided to just actually maybe we might want to just actually do some open sourcing, maybe something that we've done like maybe 10 years ago. And that might be a good way to just actually contribute to like that RISC-V from our end. Because I guess that in security world that nobody talks anything about anything straight. And like vendors are just actually very secretive about it. And but it really like that in the end, it's not that big of a deal. And maybe we did the work between like 2003 and 2008, and we can at least instantiate the same thing 10 years later to in a more of an open source form. Is that how this project had started. So we decided to just actually develop like a trust module for things like, well, I mean, mobile phone chip, generally speaking, actually does have like that, like a so-called secure element in that, like SoC, and but I don't know, even those type of stuff is not all that well publicized. So we decided to just actually do some like a trust module for like RISC-V core, like a core complex, and like specifically for things like a rocket. And then first of all, I guess we have been like since like 2013 we've been like doing this this like a software hardware consulting group, and we've been doing like just about anything that happened to be lying, coming to our end. And so we ended up doing things like board support package development, sometimes even compiler development, and then secure OS, and then things like that. We were working on that, the 32-bit, 64-bit RISC. Like for 32-bit, we just actually did our own RTL and so forth. And then, so the security and secure OS and then crypto API is something that we did before our life. So, and then, so maybe that's the stuff that we could probably do here. Essentially, what happened is like that. Initially, that this whole like secure element thing is something that came out of like that E2 PROM. People are looking for application for electrically erasable PROM. And then that happened to be like the smart card. And then things like initially they call it IC card, and then eventually got like a SIM card. And then that's essentially like the one like here, you see like that the E2 PROM and the mask ROM and RAM and CPU, and then Montgomery modulo multiplier, and then you suddenly got this security chip. And then in 1995, that Hitachi introduced like, well, initially we like Hitachi just actually did like maybe IC card and then Modulo Exponation Coprocessor, and then started doing like we started doing the Java card in the States, and we did C-Callable crypto library for the largest router company, and then like in 2008 we did the secure OS for probably the largest smartphone company. And that eventually, like that was in 2008, and then 10 years passed, and then suddenly we saw this document from that company that actually had like a huge, like volume and then completeness. And the type of stuff that we worked on was like something like this tiny authentication chip for them. And then so we are attempting to just actually recreate something like this in open source. And so we came up with this notion of like open sourcing security. And the whole background is like things like proprietary CPU designs are not disclosed. And like a meltdown and spectrum was like a bad example that why the proprietary CPU is not like suitable for like the scrutiny of like third parties. And we figured that if we open source the security, this would help transitions from security based on obscurity to one based upon let enemy know. And also open source security IPs will lower the barriers for the security systems, and then maybe nurture future nurture like the exciting application products in AI, cyber physical systems, and robotics. We came up with this like a secure module called like that crypto spec, which we named. And crypto spec is a macrocell IP, protects system and then user secrets from unauthorized access. And then this is like a crypto spec is not a sort of a single little unit, but it's deeply embedded in the 64-bit RISC-V system to prevent that the main CPUs running unauthorized software, and then by making go or no-go decision based on trust measure of the instruction and data. And it also has its own TLS software to establish its own secure connection with the server if that's how like that user wants. Like associated with it, the crypto spec is like a supply chain key solutions, which is like for like security chip or even some of the mobile chip, like you just actually generate keys, individual keys, and then inject into like that each die, and then you just actually have a setup so that like each die actually ends up having that generated keys of unique of its own. And then using that key, you can personalize this sort of like each chip, and then to be again unique. And then you can actually like by using those like keys, you can do like OTA upgrade, and then you can actually do things like remote attestations. So I guess that you could actually build up this whole solution around system, like server-based system solutions around this like secure chip too. Another thing that is like that the recent, like that now it's just very common, but in maybe 2005, 6, 8, it wasn't common, was that secure operating system. This is like the provision to just actually store long-term permanent keys and private keys into like non-volatile E2PROM flash OTP type of memory space. And RAM stores short-term keys. And privacy information is stored in the on-chip flash or external flash, like in encrypted form. And owns like SSL TLS, separate from Linux SSL TLS. And then, it has an ability to just actually download the user applications, which we call like a secure applet, which actually exists in like either the flash ESP-ROM or like the RAM. And like for that, like callback integrity check and call address list and like calling like that operating system actually requires some amount of overhead, but it is done in a secure manner. So essentially all these pieces, like applications, user applications, and then various applets, and then a secure operating system, those type of stuff, this is just actually kind of embedded in the tiny little, like a chip. And then that actually protects the keys from like being accessed in any unauthorized manner. And so like the difference is like that when we did the chip, it's a separate chip that actually like that separate from like the main CPU. But this time around, we want to deeply integrate it. And then normally like that what it does is like they call like a APDU serial interface, which is like 1-bit interface, very slow. But this time around, what we could do is, what we are planning to do is essentially using the titling switch and then have like full-fledged like the bus between like host system and then this whole like secure module, thereby doing like the things like DMA, doing things like that, like all those like symmetric crypto much faster than, like what CPU would do. Those pink part is like that essentially the rocket component. The rest are just something that comes with that secure module. And this red line that shows is like what we call like a FIPS140-2 cryptographic boundary, which is like something, like when we do that, the FIPS140-2 certification, you do need to establish this like a physical and then logical parameter that actually is like what they call like that TOE. I forgot. Huh? What's that? Target of evaluation, right? And so we are intending to just actually make it so that we can actually get clear that FIPS140-2 level 3 certification, which is beneficial to just actually get the end product into like US procurement, government procurement. And also it actually gives you some idea that how like the robust that the security system is. Well, first of all, I think that when we do something like this, we want to do like the first dev kit. So what we have first done is like maybe built a couple of chips, and then obviously like it's not state of the art, but like like we did that open RISC-V complex for 180 nanometer, and then that actually barely have one 64-bit core in it. And then next time that we are planning to do on the 65 nanometer, which will have like maybe 4 cores. But anyway, what we are trying to do is like that we build the system so that we can actually have the development system for maybe like less than $2,000 to be like delivered. And so we're working on that board on the KiCad using like a microsemi Igloo 2 FPGA. And then eventually we would like to just actually populate all these pieces on one board so that like equivalent circuit of like that SoC, like this guy here. So the pink part is like Rocket, like 4 cores, and then like all the familiar peripherals. And then we do have the secure chip that actually that's tied to the core, and then it actually does the halt and then run control of that thing. And then here's a whole bunch of stuff that you normally see in the secure chip, like true random number generator, anti-tampering little hardware, and a couple of like the CPUs, one's dedicated for like a cryptographic operation, another that's actually doing like the primarily interface and then the other duties. And FIPS140-2 certification actually requires, like particularly from level 3, like you need to have the tamper-evident coding or seals, which could mean number of things, but anyway, that's actually being defined in the spec, certification. And then like that ability to zeroize, that means like when some sort of tampering is detected, you can actually make all those keys 0. And then there are like the certain things like European EAL3 actually requires. And like we have previous experience on FIPS140-2 level 3 certification, and then we know the labs and so forth, so I think we're going to try to go through this one more time. And another thing that actually popped out was that the biendianness, particularly like that when you get the sort of government fundings and so forth, I think what happened is we have to dedicate things so that they're like the betterment of the society sort of things. And then what happened is like high-speed railroad in Japan, power plants, and various infrastructure pieces are all big endian. And then moving from big endian to little endian typically like requires fairly large amount of like the manpower. Therefore, we are attempting to just actually add big endian, which happens to be like practically you have to go through the whole thing, whole gamut of the things of like a validation on the cross tools and then operating system and so forth. And then obviously that the state side, like that RISC-V Foundation has been asked like maybe 5 times to do that the big biendian, adding big endian, but like their priority list is always filled. So you know that like that they never just like that get to the point where that the big endian is actually spoiled, like that they can work on it. So we decided to just actually organize like the OSS people, open source software people in Japan, to just actually like conduct things like doing that Spike, QEMU, UEFI, and SMP Linux, BINUtil GCC, and then all those full of things to like in Japan, so that eventually that code can be merged into that RISC-V Foundation's. So like the type of benefits that's going to bring is like on the right side, it's there's things like that side channel attack, physical attack, cyber attack, and then the attack via dev kits, and like that between like a T function or like a trusted execution function, which is yet another sort of like a larger, more user-friendly like security scheme, and then also like this whole secure element that's like a more constrained environment. We can actually address all these issues of attack, and then also at the same time we can do all sorts of things like identify real chip from fake chip, and then OTA update, remote attestation, payment support, and then multiple party application on single platform and so forth. We are planning to develop an open security system level platform with assistance from METI and NEDO. Those are like government agencies. And the benefit will be a broader reach of security technology to IoTs without fragmenting RISC-V system. The security architecture is orthogonal to existent and future RISC-V hardware. Like as RISC-V is going to just actually get the trusted execution environment support, and then maybe that OP-T support, like we don't interfere with those kind of things, but still like it gives like a functions like a root of trust, and that's necessary for those type of the features. And then we are actually have an emphasis on Japanese Cabinet Society 5.0 infrastructure application that led us to just bi-endian architecture extensions. And right now we are working with the multiple number of parties as shown in order to just actually get this one into more of a reality.